Good. Yes. Yes. So you see the slide now? I think so. Okay. So my talk is about a topic that we've been talking with David from another CSH workshop been that's been held approximately a year ago, also on thermodynamics and complex systems. And this is what we would like to show you, or we would like to discuss with you. So I have to say that these results are not definite. We have a rough draft of the paper and we haven't submitted yet, neither to archive. So we will be happy to listen to your comments. So in this talk, we will explore the relationship between two interesting aspects of thermodynamics. So first is the stochastic thermodynamics. So this is the topic of this talk. And the second is so-called generalized entropies. So sometimes these are called entropies for complex systems, and we will see whether it's true or not. So stochastic thermodynamics is, everybody knows, many speakers have presented extremely nice results, and the other will also present nice results. So it enables us to describe non-equilibrium thermodynamics by stochastic variables, especially in microscopic systems. And the results, the main results I already mentioned in the introduction talk are the fluctuation theorems, thermodynamic uncentered relations, applications to nanomotors, speed limits, etc. But there are typical aspects or typical, I would say, typical relations or assumptions. So first is that what we typically consider is the linear Markovian dynamics described by the normal master equation. The second aspect is the presence of the detailed balance, or in case of multiple baths, it's the local detailed balance, which means that the probability currents vanish for equilibrium or local equilibrium distribution. So basically you obtain that the ratio of the rate matrices of the rates is equal to this exponential of the minus difference of temperatures, difference of energies over the temperature. And of course, what we want to see is the second law of thermodynamics, so that the change of the entropy is bigger or equal than the heat flow over the temperature. Good. And now let's look a bit on the topic of generalized entropies. So generalized entropies is something that has been studied in information theory since 60s. I think Rini was the first who came with the idea of generalized entropy, and there were many other successors. It has been used in physics since 90s. I think Constantino Tsallis was the first one who generalized the concept of Shannon entropy, and then there were many successors as well, including Stefan and Rudy. This is what you've seen in the talk by Stefan. So the main aim, or not the only aim, but the main aim, really one of the most important, is to study thermodynamics of system with non-Boltzmannian equilibrium distributions. So it means that the equilibrium distribution has some other form, like typically people are interested in power laws or different or stretch exponentials, for example, and this can happen due to correlations in the system, long-range interactions, etc. So the main ingredient of generalized entropy is that you generalize somehow the form of Shannon or Boltzmann-Gibbs entropy, and you can do it in many ways. In this talk, I will stick with this definition that includes only this one sum, so it's a function of of a sum of some function of Pm, and then you use what James found it, or what James was using is the maximum entropy principle, so that then in order to obtain the equilibrium distribution, you maximize the entropy with respect to some constraints. So with respect to normalization constraint and some energy value. And the solution is this Maxent distribution. So this is the formula. So you see that the F is not appearing in the form of the entropy. So the F is not so relevant for our analysis, but let's keep it there because it's the normalization function here. And our question was for what general form of entropies the key aspects of stochastic thermodynamics hold if the system is out of equilibrium. So whether we can somehow generalize the stochastic thermodynamics to non-Boltzmannian equilibrium distributions. And we have set up several requirements to see how the elements are connected. And I will show the blue elements that are used in standard stochastic thermodynamics, while the white ones will be the generalizations taken from the theory of generalized entropies. So the first is that we take the usual definition, so the definition of internal energy, which is the ordinary definition. Here I have to mention that in generalized entropies, people somehow consider different types of constraints like escort energies, but I will not go through this because it has certain issues. So let's stick with the normal physical definition of average energy. And here we use the definition of entropy, the generalized one. Of course, if we are in ordinary stochastic thermodynamics, we will use the Shannon entropy. Good. And now the first assumption is what we call Markovian dynamics, so that we take the master equation in the following form, where the J is some functional, not determined yet, and W, Mn are the transition rates. Here it's like in a quotation marks, I would say, because in the normal master equation, linear master equation, it has you can derive it from the conditional probabilities. Here the role is not so clear, but let's call it transition rates as well. And this squared bracket, we call it probability currents, also because of the analogy with the ordinary stochastic thermodynamics. Good. The second requirement is the detailed balance. So we say that the equilibrium distribution that we obtain by the entropy maximization, for this the probability currents vanish. So it means that if we plug into this expression, then we get 0. So this is nothing else. Good. And the third one is the ordinary second law of thermodynamics. So here we take our S, which is now a generalized entropy, calculate the time derivative, and we should get two terms. So one is the entropy production rate, which should be non-negative and equal to 0 if and only if the currents vanish. And the second one should be equal to heat flow over the temperature. And now let's look what we get. So our main result is that if you consider these 3 points, then these 3 requirements imply that the form of the functional J or the form of the flow has to have the following form. So it has the form of some increasing function, and then the function in the argument there are 2 terms. So there is a function of this transition rate minus the derivative of G, which is the function appearing in the energy functional of the Pn. And I will not show the exact proof of this, I will just show the idea. The full proof is in the appendix of this presentation, and you can see it on the website. So the way how we do it is that you calculate the time derivative of the entropy, and you divide it into two terms. One is the non-negative entropy production rate. The second is the entropy flow rate, which corresponds to the heat flow over the temperature. Then you use the detailed balance. And then from the entropy flow rate, you get the constraints on the form of the current. Good. And now let's see some consequences of that. So first, let's look at the ordinary Markovian linear dynamics. Here we can rewrite this flow or this function JMN in this form. So from this, you get that the G prime n is minus log n. And when you integrate over it, you get the well-known Shannon formula, which means that that it's not a coincidence that we use the linear Markovian dynamics and the Shannon formula. This must be so because there is this thing, and it relates the dynamics and the entropy together. Okay, now let's see what happens if we consider something else. If we consider, for example, finite heat bath. So let's consider a Hamiltonian. So we have a system and a bath, and they are weakly coupled. And we consider that the Hamiltonian of the bath has the following scaling. Then you can derive the equilibrium distribution from this formula, and you get that the equilibrium distribution is equal to so-called Q exponential or Q Boltzmann factor, where the Q is determined by these scaling exponents. Good. So this is something that has been known, and if you want to get this as a maximum, as an equilibrium distribution, so then you have to maximize the Zallis entropy, which is written in this form. So from this, we get that the G prime is equal to this guy, and the master equation, or this flow, has to be written in this form. So there is no way how to make it linear in probabilities. So the consequences for that is that we have two reasonable scenarios. So either if all requirements are obeyed, so if we have Markovian dynamics, if we have detailed balance, and if we have second law of thermodynamics, it means that the system's dynamics is nonlinear. Or what we can say is that if the requirements are obeyed except requirement 1, it means that the system's dynamics is non-Markovian. So in this case, when we have non-Boltzmannian equilibrium probability distribution, then it tells us something about the dynamics of the system. So it must be either nonlinear or non-Markovian. And then, of course, there are other two possible scenarios, but I call it unreasonable because of the following reason. So if all requirements except the local or the detailed balance are obeyed, then of course the distribution obtained from entropy maximization would be a non-equilibrium steady state, because the probability currents would not vanish. But if it would be, because now it's something that we didn't want, because we really wanted to study an equilibrium state. So then when we have a non-equilibrium steady state, then we don't have to do all of this exercise. Then it can also remain within the ordinary stochastic dynamics. We are really interested in the equilibrium distribution. And of course, what theoretically could happen is that the second law of thermodynamics is not obeyed, but this is something that this would be very, very weird scenario. So actually the main idea from this talk is that non-Boltzmannian equilibrium distribution in a system satisfying detailed balance and second law forces the system to obey either nonlinear or non-Markovian dynamics. In general, the equilibrium probability distribution tells us something about the dynamics of the system. And I think, yeah, I think I'm done. So thank you for attention. And if you have any questions, please ask.